whole time it was recording. No, it wasn't. Okay, Earth science time. Today we are talking about lots of things. We are talking still about geologic time, but we're going to name this one Fossilization. Let's name it Fossilization and Early Earth. Let's name it instead Earth's History. And we're going to put in here in curly brackets, brief. This is going to be like crash course level rundown, not the YouTube series at Crash Course, but like a very, very quick, brief rundown of these things. Because I want to get through all this today, ideally. So that we have the information we need to do well on our test and in our life. But also because of that, because it's getting to be the time of the year where people are periodically or consistently gone. So let's start with the fossil record, or fossilization. To what does the phrase fossil record refer?
Is it how old the fossil is?
Okay, it has to do with the ages of fossils. Fossils here gives you a clue at the rest of it, the totality of the meaning. We could say it has to do with the age of the fossil. What else does the fossil record have to do with? Let's make it even more basic.
How big?
In general, what is fossils about? Or the what on Earth?
The dead things. Well, not the dead things, but
the things that were once
alive.
Yeah, ancient life. And the fossil record is what we use to refer to let's say, let's put all fossils and what they tell us. That's how I would describe it to maybe not a 6-year-old, but a 6-year-old who knew about dinosaurs, or like an 8 or 9-year-old who didn't know about dinosaurs. I would say all fossils and what they tell us. Like it's the preponderance of the fossils. It's every fossil discovery and what it tells us. That's the fossil record. So when we say the fossil record is evidence of a certain event in the Cenozoic, that means that we're using fossils to tell us about that event. And we're not using all the fossils, but that's within the realm of possibility. Like that totality of evidence is what we use for that. One of the things that will be on your exam that you need to be aware of its existence, or like how it works, that I'm assuming you already know, because that's one of the reasons biology is supposed to be a prerequisite for this class, is that, let me start a new bulleted list here. The evolution of biology on planet Earth. Evolution and biology. You just need to know both of these things, because as you're aware there's some degree of strife around the topic of evolution still. One of the ways that my college professor when I took biological synthesis, which is an evolution class, the way she described this is that nothing in our current understanding of biology works without this robust definition of evolution. That the way we currently understand biology doesn't really work if we don't have a definition of evolution somewhere therein. That things have to change in order for anything to make sense. And that's what it is at the most basic level, that life changes. I don't mean an individual's life changes, although that's true too, but that's not evolution. That life, the whole zoos, as I said yesterday, the whole idea of life, the life was different before, the entirety of life. Like if we go back far enough in the past, there weren't human beings. If we go back even further, there weren't multi-celled creatures. And that's the only way that biology is really understandable, is if we also know about evolution. That obviously relates to the fossil record, because as things evolve, they change. And as things change, they become either better or worse for their environment, and many of them die. And whole groups of them die, and that's called what? What do we call it when a whole group, or as Tegan Prosser, you know her? They did this unit in 8th grade science, which is, the fact that we do this in 8th grade science is why I know that you should know this, and probably do know this. But when they were defining their words for the unit on Earth's history, Tegan Prosser misread one of the words and wrote, "The death of every memory of a species." And I thought that was beautiful. But it's actually the death of every member of a species is extinction. And then what would make it a mass extinction?
Isn't it like whatever percent of
Yeah.
all life is?
Lots
No, what?
of extinctions. What causes this kind of thing?
It could be like a volcano blowing
Yeah,
up like
well,
the dinosaurs.
probably not a volcano.
No.
A volcano has a very low likelihood of even causing one thing to go extinct. But a period of mass volcanism could cause mass extinction. And a time, I mean, when lots of volcanoes are going off lots of the time, sometimes even for millions of years, can change the climate enough that those things are no longer well suited for their environment and lots of them die. In the largest mass extinction events, something like 99% of individuals died and something like 90% of all species were extinct. It can be very, very, very severe. This is a little side note, I'm not going to write it down, but the evidence suggests that this is a mass extinction, that you and I are living during, I wouldn't say through, because we won't still be alive when it concludes, but we are living during a mass extinction event. In fact, the fossil record, the totality of fossil evidence suggests that in the world's, what we think, the evidence suggests the world's worst extinction, history's worst extinction event, where, like I said, 99% of individuals died, 97% of all species in the ocean, and 75% of species on land went extinct. That right now, things are going extinct more rapidly than they were during that time. So this might be the worst mass extinction event. Probably, this gets into sketchy political ground, but probably caused by human beings, at least to some degree caused by human beings. Is that degree 1% or 99%? That's not the point of this class. But to some degree, human beings are contributing to this. When I say 1%, if you even think about human beings literally killing all the dodos, we watched that happen, right? That's recorded in human history. That would be not 1%, but something on the very, very low end. If we only accept that was true, human beings definitely contribute at least a little bit. And if we assume on the very, very egregious end that we're causing an awful lot of things to go extinct because of climate change, but somewhere in there is probably the truth. It's probably not we're going to make everything die, and it's probably not we only killed the dodos. But somewhere between there is the truth, and it is definitely, the evidence suggests, why would this be a difficult thing to show? Like, why would it be hard? Why can't I just Google, is this a mass extinction? Why do we need 90,000 research papers telling me here's the evidence for it? Why is this something I have to collect evidence for? What's true of mass extinctions usually? That makes it hard to know. Let me get a more pointed question. Why is it hard to know if we're living in a mass extinction right now?
Well, like all the mass extinctions that like we think of or we've known from in the past, like in history, I mean, they weren't just like living their normal lives. Like the dinosaurs weren't just living their normal lives when their mass extinction
Exactly.
was coming.
Yeah, heck yeah. That's what it's the same thing that like when Andy Bernard in the office says, I wish there was a way of knowing you were in the good old days before they become the good old days. It's that exact thing. Like, I'm living through this time now. So it's very difficult for me to say this is good or bad. In the same way, we are currently living through a mass extinction, so it's very difficult to say. And also, they take a long time. Just like the same thing with the good old days. You know, your whole life, maybe you'll live to be 200, I don't know. But when you're old and gray, you'll look back and say, oh, those were the good old days. But while you're in them, they don't feel good or old because it's right now. While we're in a mass extinction, it doesn't feel mass because there's a squirrel out there, for crying out loud. Let's talk about how fossils are made. Let's erase this and talk about how fossils are made. I got a little bit on a soapbox there, but you'll have to forgive me because I do that sometimes. Let's talk about how fossils are made. How do you think of fossils being made? Like when you think of fossil from Animal Crossing or whatever, how do you think of that being made?
It just shows up with a star on it.
Yeah. Let's draw one here. We got this little kind of roughly circular shape, and it has one of these little boys, and it has one of these little boys, and there's like some dots down here. That's a fossil, obviously.
Yeah.
And how do you know there's a fossil there? Well, there's this star-shaped crack in the ground, and you shovel it, and then you turn it into the owl, and he says, you got a freaking pachycephalosaur, and you say, nice. Actually, I'm missing one from my museum, and it is the Spinosaurus torso. And I have been missing it since like
I have every
June
single
2020. Shut up, don't knock me. Yeah. No. So in real life, though, how does a thing become a fossil? I love this question. Dally Andrews got a little bit frustrated when I asked her this, but I'll tell you about that in a second. Let's imagine, y'all are hunters, right? Tristan, I assume, hunts. If there were a coyote running across the football field right now, look out there. Do you see it? This is called
Oh my gosh.
It's called imagination.
The coyotes.
Okay, you see the coyote running around out there? Now, imagine Tristan gets out his .30-06, much too large a caliber firearm to be destroying coyotes, but he shoots the coyote and it dies, okay? That's the first step in fossilization. The thing has to be dead. But the coyote has dead, and now imagine Jason takes the rest of the year off, no one does anything with the football field, the coyote is just sitting there. What will be left? What? Okay, go on.
And, well, in our explorations, it said that, like, nothing can get to it. Like, nothing can eat the dead body.
I'm doing the opposite of that right now. So imagine no human beings touch it, but otherwise we leave it alone. Other coyotes can eat it, which they will. A little bit icky, but they will. What will be left in a year? If that happens, if Tristan were here, which he would do this if he were here, I guarantee it. If there were a coyote outside, and Tristan were here, and he were allowed to have a .30-06 in school, the coyote would be dead. March 22nd, 2023, RIP. If we came back March 22nd, 2024, what would be left?
The bones.
Try again.
Nothing.
Nothing.
Oh.
You would not see anything. The thing would still, like those atoms that made it up would still exist. It would be in the dirt and in the other organisms, but there would be nothing left. There would be no evidence. So how come, that's what makes this so special. If that weren't true, think about 4.5, well, I was going to say 4.5 billion years of Earth's history, which is true, but think about 3 billion years of life history. If it was true that everything that died just became bones, you couldn't walk an inch without tripping over a whole pile of bones. So most of the time, like a large amount of the time, let's say 90 to 99% of the time, that's an estimate, most of the time, no evidence remains after death, after biological death. So now that explains part of why fossils are so rare, and it does a pretty good job of explaining why older fossils are rarer. Fossils are rarer. There's more fossils. I'm throwing this out there. I think this is true. There are more fossils of mammoths than there are of Tyrannosaurus rex. Why? Were there more mammoths when mammoths were alive than Tyrannosaurus rex? Is that what that tells us?
No.
Probably not. That might be true. That's not what that tells us, because what it really tells us is that the mammoths existed more recently, and so their remains have had less time to destroy, because even fossils eventually degrade. So usually, nothing happens. What has to, this is what Kyle is getting at, what has to happen, let's make a list of 3 things. I don't know if this is not like the 10 Commandments. This isn't, these are the 3 things that must happen. But let's make a list of 3 things that might make it easier for a thing to become a fossil. Remember, a fossil, we haven't actually defined this yet, but you should remember from your explorations or from when you were in 8th grade, that a fossil is just any preserved remains of an organism that is greater than 10,000 years old, is the usually agreed upon definition. We don't say like, like if you hit a hobo with your car and you just drag him off the road, he's dead, and you drag him off the road. That's not a fossil. Usually things we consider have to be 10,000 years old, and it's any evidence of life that's more than 10,000 years old. Once again, on the other side, it doesn't have to be the remains of an actual organism. It could be like a footprint. It could be eggs. It could be poop, which we call a coprolite. And those things are all evidence of life, but they're not themselves were ever alive. Anyway, what are 3 things that would make it so the fossilization would be more likely to occur than just leaving it out there?
Like nothing touches the...
Why would that ever happen? I mean, like, let's make a physical reason why.
I was talking about how, like, if another animal goes and eats it, and then that animal's bacteria gets on the decaying body, then it could mess up the...
Yeah, so what physical processes could happen so that doesn't occur, though? Usually what?
It could
Yeah,
go underground.
Yeah, what do you call it when a thing goes up? It's dead, so it doesn't like scooch its little zombie self under the ground. But what could it, this is the other way around. The ground goes on it. What do we call that? Burial. Is this related to the anthropological reason why humans prefer to bury their dead? I don't know. I would probably somewhat relate it. Like you don't want to, if your aunt dies, you don't want to just watch the remaining husk of what she was decay over time. The burial at least removes it from your sight, but also slightly preserves it. Okay, what else? In what? Burial in what?
Soil?
Yeah, it could be in sediment.
Yeah.
It could be in something like tar or mud. Could it be in lava? No, it couldn't be in lava. Why could it not be in lava?
Because it would have burned.
Yeah, because it would be on fire, and then that would not be a good way of preserving it. And that gives us something else. In what kind of rock would we probably find fossils?
Sedimentary.
Sedimentary. We're not going to go to the center of the Black Hills, where there are 2 billion year old metamorphic and igneous rocks to look for fossils. We wouldn't find 2 billion year old life. We would find igneous and metamorphic rocks without life. So we usually look in sedimentary rocks. And then also, do you think, I'll just tell you, the burial has to be rapid, or it almost always has to be rapid in order for fossils to form.
Okay, but what about, like Pompeii, the ash? What would that...
Burial. They were buried in ash. Those people, those are not fossils because they were human beings.
But it preserved it still.
Yeah, it's preserved as fossils would be. Because it was buried, in that case, in ash. So we could put ash on here. Oh, I see what you're getting at. Like you would say, you're saying that maybe it could be an igneous or metamorphic rock. Ashfall still constitutes sedimentary rock because ash counts as sediment that then can collapse into a sedimentary rock.
Hardened on to like everyone and everything.
Yep. Yeah, so that ash burial is still burial, and it would still be a sedimentary rock, and that would be super rapid. Like the people, there's evidence that those people, and they're not fossils, like I said, but those people were in the midst of just doing stuff. Like they weren't doing normal stuff because they knew a volcano was erupting, but they were like walking or sleeping or like crying and snuggling their loved ones because they knew they were going to die, and but they're frozen like that. As they and that tells us it probably wasn't over the course of like 10 hours. They were just like dead and not quite fossilized, but become ash. Oop. Oh no. I was trying to do that for emphasis and I really overemphasized it. Let's talk about some different types of fossil preservation. The rarest is original soft parts. Why would that be rare? And how could it even happen? Like, why would it be rare is an easier question to answer than how could it ever happen. Why would it be rare for original soft parts to be preserved?
It's kind of like...
They're
soft.
They're soft. A thing wants to eat them. Whether that thing is a coyote or a bacteria or whatever, but that's the part that will decay the most rapidly. That coyote, in our example, if we came back a week later, I would say most of its soft parts would be gone. I would say if we came back 2 hours later, its eyes would probably be gone. They're just right there. Something's going to come eat them. So original soft parts is very difficult. How could that ever happen, though? I mean, like when we talk about an hour later its eyes are gone, probably a week later most of its soft parts are gone. How could it ever happen that we could, like in Jurassic Park, have a mosquito with original soft parts?
Because it makes me think of how they, like when ants are preserved in amber or something like that, they're preserved in certain things.
Amber and tar are really the only ways that there are probably others, but amber and tar are the only ones I'm aware of that would offer original soft part, especially for things that are on the order of millions or even billions of years old. Something kind of cool about this is that usually it is insects that are preserved in amber, although there's a fantastic example of a Chinese dinosaur that was found. The dinosaur wasn't Chinese. It was found in China. The fossil is Chinese. The dinosaur was found preserved in amber, or not the whole thing, but part of this relatively small dinosaur was found preserved in amber. And guess what it had on it? Because it's original soft parts, which is very, very rare for a large organism. It's rare for insects, but it's very, very rare for a large organism like a dinosaur, even though the dinosaur's like this big. But that's still rare. I mean, that's a lot of amber. That's a big chunk of amber. What was found on that dinosaur? I think I've told you this before. What soft parts did we have direct evidence for the first time that I'm aware of? No. It was its tail. And that's on the answer. I'm saying that the part that was preserved of it was its tail. What did we find on this dinosaur? Guess, keep guessing. Skin, yes, but no? No, better than that. No, better than that. For the first time ever, we had direct evidence that the dinosaurs, at least the Cretaceous dinosaurs, all, or most, had feathers. Yeah, it had feathers. And since that's a soft part, and since we hadn't ever seen the original soft parts of dinosaurs before, people were like, is this imprint of the mark of a feather or is it a scale or whatever? There was discussion like that. But now, we know, at least, we are 100% sure that at least that dinosaur and at least its tail had feathers. But we can extrapolate that to probably all Cretaceous dinosaurs had feathers. Which is actually, and at first, when I first found out dinosaurs might have feathers when I was like in 6th grade, I was like, stupid, that's stupid, I will never accept this. But then you look at pictures that people have drawn of feathered dinosaurs, like good ones, and they are beautiful. I mean, you can, because birds are beautiful, and dinosaurs are birds. All the dinosaurs, we separate, by definition, we separate dinosaurs from birds as the dinosaurs all died when that meteor hit, and the birds are the ones that lived. So really, in a biological sense, the dinosaurs, the ones that lived became birds. They didn't stop being dinosaurs and start being birds. They are the same thing. When you eat dino nuggies, you are eating dinos. And if you don't think that's poetic, then you can get out of my face. The fact that we mentioned original soft parts implies that there is also original hard parts. Give me some examples. What do you think? What would hard parts be?
Like bone.
Bone.
Like fingernails? Maybe?
Nails, yeah, claws, nails. Teeth. Shells. We don't have shells, but some organisms do. Even that's pretty rare because the hard parts that make you up, or that make most organisms up, are really actually soft on the Mohs scale of mineral hardness. Like the hydroxyapatite, or if you brush your teeth, the fluorapatite that makes up your teeth, is only, I think it's an 8, that's fairly high. I mean, it might be 7, it might even be 6.5. But that's fairly high, but over time, even quartz will degrade that. And so even in the course of, whereas the hard parts in an hour to a week are mostly gone, the hard parts, even if they're buried, are oftentimes eroded away within hundreds or thousands of years. So even this original hard parts is fairly rare. Where do we get most fossils from then? Yes, but what method of fossil preservation? If it's not, when you even see the dinosaur, like I've seen a Tyrannosaurus Rex excavation, those are not its bones. They're the shape of its bones, but that's not bone. What is it? It's rock, and we call this permineralization. This is maybe not the most common, but it's probably the best method of, or the one that people think of the most is permineralization. And what happens is, you're full of little holes. We've talked about absorbed in yellow and porous heat, right? You're full of pores. Some of us have pores on our noses. The super complexion girls don't have pores on their noses, or so I'm led to believe from TikTok. But the rest of us, we mortals, have pores all throughout us, even in our bones. And so a lot of times, well, for a fossil, which remember, very, very rare, but a lot of times when a fossil is preserved, it's because that bone has been saturated with mud or some mineral dissolved in water, and that mineral or the mineral water gets into the holes in the bone. And then even though the bone degrades, that mineral is still where those holes were, and it forms the shape of the bone. And so when I saw a Tyrannosaurus Rex being excavated, it wasn't its actual bones that they're excavating, it's rocks in the shape of its bones. But that still tells us about it, right? You see how that's still a wonderful thing to know about. That's called permineralization. It's sometimes called petrification. It's sometimes, there are some different types of permineralization. Mineral replacement is where minerals from the environment are fill in the holes. Recrystallization is where that same mineral that makes up the bone or shell or whatever recrystallizes into a harder version within the pore spaces, and either of those count as permineralization. Another one, and I think this will be the last one we talk about, is cast and mold. And a cast is it probably should be the other way, mold and cast. The mold is the negative space impression, so this is like footprints often form these. If there's some sticky mud, you put your foot in it. There's now the shape of the print of your boot is in the mud, but where it was a lump, there is a hole. It's a negative space impression, which means it's the opposite. Where there was something sticky-uppy, now there's something whole, right? And so a mold is when, a shell or something gets pressed into sediment, and then a cast happens when that hole gets filled in with new sediment, and now it forms this shape. Does that make sense? So then in my boot example, the boot makes a hole where there was a lump in the mud, and then if maybe snow comes and fills that in. This would not be a very good fossil because snow doesn't do a good job preserving things, but snow comes and fills that in, and if you were to be able to carefully remove that snow, now that snow is the cast. It would have the same shape. It's a positive space impression. It would have the same shape as your boot. The lump would be a lump. Yeah? We did this in 8th grade science this year. It worked a little bit better than when we did it last year. Not great though. But what they do is they press something into some clay, they fill the hole with plaster of Paris, and then they let the plaster dry, and now the plaster of Paris has the same shape as the original thing did. So really all we got today is fossils. So one out of the 4 things I want to talk about. The other 3 things that we were going to talk about, and now we'll do another time, are just the nature of how Earth was in the Paleozoic, Mesozoic, and Cenozoic eras of the Phanerozoic eon. Do you have questions about fossils, though? You know about fossils, Neil?